discuss a quick question about the previous slide?
Sure.
About generative models. So if you have a pretty good generative model that models a perfect class in all the physics, would you be happy putting in some kind of a threshold and saying anything that's
outside of that? So if you have a, let's say you have a perfect generative model, it exactly generates all your positive data, okay? Then still thresholding that can be problematic. So yes, you can, but a generative model still will actually go. this allows us to just threshold this value in the next moment. Now, that's fine for a single point, but of course, hello, is that working? Well, if it dies again, let me know and I'll. Is that better? Yeah. Okay. And I'm back to green. So if we have a single point, that compact abating thing was simple, but we want to actually be able to prove more powerful properties. So we came up with this idea of which is really simple stuff. We just built a fusion operator that can take a bunch of such kernels, and then again you can add some probability to those, and that gives us a model. So this is what we call a an abating probabilistic point model. It takes a bunch of individual points, fuses them together, and we'll show some properties in a second about what this lets us do. So once we've done this, we can actually prove that that sum is itself still abating with a slightly larger bound. So if I take a bunch of abating functions, combine them in a positive set of sums, or maximum some other functions, we can still get an abating bound, which means we can continue to prove some simple things about them. So this gives us finally this idea of the compact abating probabilistic model, where if I take my, I'm trying to use my mouse again, so used to that from class. If I take the minimum distance between points and I say if they're greater than tau, if I have a compact abating probability, as I reduce tau, I can drive this threshold, as I reduce my threshold tau, I can drive the probabilistic threshold down to 0. This means I can make my open space risk as small as I want. That's not a perfect solution because I now have to balance open space risk and empirical risk. But it means I can balance it all so that my open space risk is as small as I want, which gives me the full range of adjustments that I will need to make stuff happen. From this, then, we get the following theorem. I guess it doesn't actually help because I can't use the mouse. We have our stop using the mouse. So we have our compact abating model. If we let that be our probabilistic recognition function and uses a CAP model, so over a known training set, then simply, if we let the open space risk be R0 of f and the open space risk be 0, then if tau, or if R satisfies, remember R was that parameter that bounded the definition of open space. It's the size of the ball around each point. So if R is such that R is greater than tau, then the open set risk is at 0. Because we can shrink these down and there's a ball of size R around every positive point. At that point, we've captured some of the positive data, but we have 0 open space risk. And so this allows us to trade off between those two parameters. So what does this really mean? Well, it means that as we reduce the cap threshold, we reduce it so that it's small the open space radius, then the cap model will have 0 open space risk. Okay. So we actually have in the slides proof, but does anyone want to see a proof? Walter does. You've already seen it before. Okay, we have one person. Okay, I'll go through the proof. Okay, the proof may help intuition, may not. So there's nobody get my mouse out here. Okay, it's just so hard for me to turn around anymore. So if we let x be some point in open space, so it's out there in our open space, that implies that x is not in the union of the points within radius r of any of the known data. That's the definition of x is in open space. Okay, but for that point, we can now say that for all of the x's that are known data, the known data, the distance between x and x of I has got to be greater than r. Otherwise, it would be in one of these balls, but it's not. By the assumptions of the theorem, r is greater than tau. Therefore, by the compact abating property, the m will have to be m tau of x is equal to 0, and that comes from when we define the right, compact evading model, right? Set at this point, right? The points were greater than this imply that this was 0, and that's because we've now taken it below our threshold. So when we go to do our theorem, as soon as it's in the open space, this relationship here, that its distance is greater than tau, means it has 0 probability. Putting that in the numerator of the formula for risk, right? So now this part is 0, right? Because that's the integral of the indicator function over the open space, and now that for that point is 0. So that gives us that our overall open space. So as long as r is greater than tau, so that when we reach our threshold it will be 0, the overall open space risk is true. In doing this, right, we did this for, I'm sorry, this is still in the theorem. Right, we did this for any point x that's in the thing, but since that's true for any point x in the open space, as I integrate over all of that, it has to be 0 because it was 0 for every one of them. So when I take the integral of, doesn't matter how many zeros I get, I still get the overall integral of 0. And so that shows that we've now managed our open space risk. So the corollary of that, which is pretty easy to remember, the thresholding of a CAP model's probability manages open space risk. So if your generative model actually had this nice probabilistic CAP property, then thresholding it gives you open space risk. But now it depends on what's the structure of your open space or your generative model, which may or may not have that property. Okay. This is a sufficient but not necessary condition to manage open space risk, which we'll come back to. So I'm not going to read through all of this. So how do we get from corollary 1 to an algorithm, right? So the algorithm we have, this thresholding, it gets us there. Well, the problem is we have no guarantee that the model assigns positive labels within the compact region. As I said, we can manage open space risk down to 0, but if I don't label the positive things positive, I still have a really bad algorithm. The algorithm that always answers no, right, manages open space risk. It's the trivial classifier, just say no. Problem is it also doesn't get anything right in terms of positives, so not a very good algorithm overall. So we have to figure out how to make that part better. The quality of the CAP model will therefore depend on how well we do in modeling the probabilities of the actual underlying positive region. So a first thing we did along the path in this paper was to think of something a little smarter. So we took a one-class SVM and a nonlinear RBF kernel. The nonlinear kernel we know is good. The problem is that the nonlinear RBF kernel doesn't bound open space risk. Because, in fact, if I have a binary RBF, one of the two sides of the binary side will have infinite support. The other may or may not be. But we know that one classes, when properly thresholded, can be. So we actually have another theorem from that paper where if I take an RBF one-class SVM and I threshold it, that yields a CAP model. Right? So that gives me a CAP model. So if I take my training data, and I'm going to call this thing the OSVM for the one-class SVM, be this one-class SVM with a square integral monotonically decreasing RBF, like a Gaussian. But any other monotonically decreasing RBF would be okay. Defined over the training data, if I have its associated Lagrange multipliers alpha I greater than 0, then the kernel, which becomes the sum of alpha I, yi, with the kernel, where yi is now the positive data only, because this is a one-class SVM, all the data is positive, then this is a sum of positive constants times an RBF kernel, or properly a CAP-type kernel, and the sums of those is itself a CAP model. So there's a bounding capability there. So taking any one-class SVM and thresholding it naturally gives us a one-class model, gives us a CAP model, which bounds our open space risk. So coming back to our intuition, which is where sort of part of where Walter started, is like one classes solve this problem. They basically define a nice region. It's actually only true if the one class has all of my properties. There's a few degenerate cases where the alpha i's won't satisfy this formula, but for an RBF SVM, one class SVM, they will. And I'm going to skip over that too, given our time. So that was nice for one class. I go to the end of the deck, right? Okay. So given that we've defined it for the single class, now we have to talk about the more general problem. What happens when I have multi-class open set recognition? So I have a bunch of known classes, but around them might be unknown classes. And in fact, here I've drawn them in a nice simple way that the classes don't even overlap, but in lots of multi-class problems, the classes overlap each other a little bit. Unknowns might overlap the classes, so we have to be able to handle all of these. So we really wanted to generalize this concept we had from the CAP model. And so what we're going to do is define this compact abating probability in a way that lets us generalize for a multi-class problem. So for every class now, we want a probability for that class to be decreasing away from its positive support data. So for every positive class, we go back and try and find the kind of model we want. So there's some known samples. If you think about putting positive lumps around those, and then as I get farther away from those lumps, my overall probability has to decrease. And then if I threshold that someplace, I will again have this compact region in space where I have sufficient probability for that class to be positive. Okay? And since these are all, we're assuming stuff, they're all going to be abating functions, they're all decreasing. If I do this for every class, and then I threshold all of them, and I maybe take the maximum class, then we get a nice multi-class compact abating probability model that allows us to solve a multi-class problem. So this is our paper from 2014? 2014. So we might also think about this and say, well, how's this related to anything? Like, did we really come up with something really new here? And in one level, we're trying to formalize this open set stuff, but the problem of open set, as Walter already said, existed long before us. People have been struggling with what do I do with these unknowns. So there have been things much earlier than that. For example, kernel density estimators are sort of one class type thing where you fit a Gaussian distribution to the positive data for a class, and then you somehow empirically estimate a threshold over the density. And you say, okay, I'm in a region where I've estimated a density, and therefore that's a probability. Now, I don't know if you consider this a generative model or not. Some people do, some people don't. But, well, actually, to me, it's only a really generative model if there's a physical reason to say it is. But that's why you said physics before. So here I have a bunch of samples, and so now I can threshold them. And if I just put Gaussians around my samples and threshold them, it is a compact abating probability, but it might not be a very good one. So if I take, so here's, so you got to remember this. So the blue here are some points. You put down a bunch of Gaussians around them. This red thing here is the actual KDE density model, right? That's the real. Sorry, that's the real distribution. The Gaussians, the sort of smooth curves, are the fit Gaussians you get to them. And now, for this problem, you have to choose what's the right Gaussian width. There's a bandwidth for the variations, and then how I put all the points down. But you can take that and then choose some threshold. And if I choose this threshold, I'll get one region. If I choose a different threshold, I'll get very different. So if I'm looking at these, like the green Gaussian, at this threshold it finds nothing. At this threshold it gets a much broader region than where you want to be. And those are all trade-offs. So the idea of kernel density estimation has been around. It generally results in overfitting for visual recognition problems because it tends to have all these narrow little regions you want to get around of. The choice of the Gaussian distribution is questionable in many circumstances. Why is a Gaussian the right distribution for your data? And there are reasons for using the central limit theorem, but they don't necessarily apply when you're doing density estimation. And then finally, how do you get a good estimate of tau? But this idea has been around, and so what we're looking at is a process that actually might be far more discriminative and more powerful in terms of where we want to go. Another related idea is the idea of a support vector data descriptor, SVDD, which came out of Tax and Dewin. Doesn't actually have the year here. Was it 2001? Yeah, so around the same time here. And that's basically the idea here is to fit a hypersphere with a minimal radius around the positive class, but it's not quite around the positive class. It's most of the positive class getting all, almost all the trading points. So they define a reasonable fast formula for doing this, where you can try and get a hypersphere that is centered around the data and has a radius that gets most of the data inside, but there can still be some outliers. Because this is a ball centered at a single point, and if you're in it, you're inside the class, and if you're out, you're outside the class, it is definitely a compact abating. Sorry, it definitely solves the open set risk problem because it's a bounded compact space. Okay, it doesn't have zero open space risk. It can't be driven to zero unless you drive the radius down. Their algorithm won't necessarily drive the radius down, but it will allow you to at least bound your open space risk. By far the most dangerous thing is when your open space risk is infinite because you label tons of stuff. If it's finite, at least you have some balance in where you've gone. So this algorithm is, however, unfortunately sensitive to feature scalings, and it's nonlinear in terms of how that sensitivity comes up. It's difficult to solve using good numerical optimization techniques, and it's in practice been shown to be far less effective than binary classifiers when some negatives are available. So SVDD is another kind of one class. You can train it with just the positive data. But as soon as you have negative data, it's not near as effective. In fact, I would say now by far the most common use of this is mixing it with something else. So it does one kind of bounding, and then you put it together with some other approaches. There's Trigg's paper, or whatever. Somebody in Trigg's did a paper where they combined this with some planes and whatever. So that's out there. And as Walter's already mentioned, the one-class SVMs, also from the 2000-ish age, is a very formal way of looking at this. It uses only the positive training data. It defines the origin as in the kernel space as the only other member of the second class. So the one class actually uses a negative point by saying we're going to treat the origin as negative. And then it defines a binary classifier using that, and then is able to get the things. And when you're using it for anomaly or outlier detections, it's what people think is their only choice of what they can do. But it can be problematic. So if I take some positive data, all the black dots here are positive. By the time I include the origin, if I'm doing a soft margin classifier, it may capture some of the positive points as negatives because it needs more support vectors to make things balance out in terms of what it's doing. And that comes just from the nature of trying to do the one-class SVM's objective function. So here we have the standard minimize the norm of our weight vector. We have some regularization parameter and our slack parameters, and then an offset parameterizing hyperplane because we want to make sure that the origin is not in the positive data because that's going to be the point we make negative. So if we didn't offset it someplace, then we get this problem. So one of the problems we've seen in practice trying to deal with one-class SVM is it can actually be quite sensitive to this parameter, and if I take my data and I move it around, I get very different answers, which is a little bit disconcerting, especially since the one thing people like to do is sort of normalize the data so it's mean 0 and plus or minus 1. Well, if 0 is your negative point, you can't do that. So you got to figure out how to mean shift it someplace else, and you get some behaviors that may not be intuitive in terms of what you've been playing with and everything else. So, so this parameter nu, which is here, right, is a regularization parameter, controls the upper bound of the training error. But in terms of the test error, it's often very, very weak in what it can do. But it's very easy to use. You just go to your favorite SVM implementation like libsvm, and you basically get to choose one of the types. So your SVM type here is your -S2, and you get a one-class SVM. So it's easy to stick this in and try it. The problem is, as many people have already found, didn't really catch on. So in Zhu and Wang that Walter already mentioned, the parameters are just very difficult to get right. The Gaussian parameters tend to lead to overfitting. If you choose them in an automatic fashion, they're problematic. Even if you choose them using cross-validation and you get slightly different data, they tend not to work very well. So the cross-validation of those parameters is more difficult. And this is true outside of our field. It's true in a bunch of other problems as well. So one class gets used. It's still cited every now and then because it's often the best choice people get. But we wanted to do something better. So let's look at some of the problems that come up with the traditional binary types of classifiers. So here I have two sets of data, the ones and the twos. And the sort of pink outline here shows you the one class SVM RBF decision boundary where we've done grid search to find the best parameters to give us the best fit to the class 1. And you were looking at this saying, oh, but it's wrong. It's got all these twos in it. The problem is the one class doesn't use twos. It only uses ones. So it's trying to find this nice small circle that just includes all of the data for the class 1. But if I use it for that, and it has these three red circles for the one class SVM support vectors, it's very generic. So it's going to end up including a bunch of points that aren't in it because it doesn't know to ignore those. On the other hand, if I take the binary SVM, I get all of these blue squares as the support vectors for class 1. There's actually some support vectors for class 2, but I'm just showing the positive ones. And this whole blue region will be marked as positive. And that's problematic because there's these points here that are far away. In fact, there's these points over here. Oh, hey, nice timing. Right. These points over here are also marked blue. Those over there, right? Upstairs. So somebody next door is leaning against the knobs control the entire building. They're not well separated. Sorry. It's an open set problem. They don't know they're adjusting our lights. So if we look at these as surfaces in terms of the normalized decision scores, here's what I get for the one class SVM to sort of put it, give you some intuition. So here's our surface of the probability of being in a positive class that the one class SVM has. All the ones are up here, and they sort of pull the surface up. And that's all it gets to do. It wants to keep the origin, which is probably someplace over here, negative, pull these guys up. But it does a good job of at least rejecting these question marks. So it didn't get the outliers included in the class. The problem is, if we go back, right, it included a lot of these other classes, right, because it just doesn't know any better. So on the other hand, if I look at the binary SVM, it has all the ones up here. It pulled the surface up, has the twos here, but overall the bias of this plane brought the whole plane up so that almost everything except for this small circle here is labeled negative. And all this became positive. And so that's another problem we have, is that we can't put these two together. Later on today, we'll talk about some recent work from a group out of Campinas that is trying to address this problem in terms of how to solve problems with just regular SVM. So there's a whole bunch of other techniques in terms of techniques that have tried to begin to look at the open set problem. So looking at them in terms of zero-shot learning and detecting unseen classes. All of these are trying to address the same kind of problem. One-shot learning is a particularly related concept because what I'm really trying to say is I want to learn from one example or one example of a class. That problem is particularly subject to unknown unknowns because you're assuming this represents everything. The number of negatives you can get is really difficult to deal with. So you have to be able to go through and work through those. Last year, Abhijit Bendali and I had a paper on what we call open world recognition, which is now sort of taking this, everything we've talked about so far, to the next step, which is really where I wanted to go, but we have to do it piece by piece. So if I start with my world has knowns and unknowns, okay, I can do two things. First of all, I can just recognize something as known, which sort of comes out here. That's our normal thing. But what do I do after I've detected something as unknown? So I've now got my open set algorithm and it says, this is unknown. Now what? Well, given that it's unknown, I can collect a bunch of these novel unknowns and somehow, magically, we go get the data labeled, maybe through Mechanical Turk, maybe through graduate students, maybe through actually clustering and lots of other things. We're not going to say how that happens. But now we can take these unknowns and we want to incrementally learn those classes and add them to what is known. So now comes the next question. Can we actually have one of these algorithms that is easily amenable to not only detecting unknowns, but then incrementally learning as we add new things? And that becomes another challenge for us to deal with. So we've already seen our class where out in the real world we have a bunch of things, right? And we want to be able to recognize these unknown things, but we probably need to actually detect that it's a new category and add it into our representation and then do that for every new category. I see a couple of these and some of these, maybe I don't care about mushrooms, might not care about that, but I might see some other things and all of a sudden have to learn, okay, I do care about pool tables, bulletfish. We need to incrementally learn these new things. And we relate this now to the problem as we call open world learning, which is a combination of open set learning, incremental learning, and actually if we want to do it meaningfully, we want to be scalable. And so there's a whole bunch of people who have looked at incremental scalable learning, a few people, mostly us, who have looked at open set learning, and then a whole bunch of other people who have looked at just pure scalable stuff. And so you want to put all those things together to build open world learning. So again, coming back to the CAP model, we already talked about if I take this and I threshold it. So in this case, we're going to have a very simple, we're going to try and build a very simple but highly incremental algorithm, which is based on a class mean. So if I have a class mean and I put a single Gaussian around it, say a standard deviation, and I threshold that, then a single Gaussian is monotonically decreasing, it's centered on a class mean, and I now have an algorithm that I can easily do. In fact, any tented function that goes down, right, even a linear tent, ooh, look, will work out. So one of the questions there is, well, that's fine. So we wanted to have two other things we needed. We had to have a couple other things so that we could show what we wanted to in our paper. So we extended the theorem on open space risk to a very simple combination. Before we had combinations that were sums. We showed that a combination that's also a maximum or any other monotonically enhancing function also allows us to balance open space risk. And the one that was more important for this is any linear transformation. So as long as it's dimension it's dimension preserving or projecting, any linear transformations, for example, any type of metric learning, will also be, if I manage risk in this space, I will manage risk in this space. And by manage, I mean I can drive it arbitrarily small. Okay, so if I take this, and then really, if I really think about this, is I have some monotonic function that's decaying. If I sliced it, I get some sort of ellipsoidal shape and whatever. In transform space, I'm still going to get some compact projection of that space. So I'll get a nice compact space. Now the volume of these two could be very, very different because I could project down in space, and so the dimensions could be very, very high. But it allows me to at least manage open space risk. And that became the fundamental set of added tools. So now we have some theorems that let us manage open space risk by saying anything I can do with a compact abating probability goes down, I can limit that. If I take anything that now takes sums of those, maximums of those, linear transformations of those, so a whole space of transformations to these things you can prove are abating, combining those together still gives me abating algorithms. And that gives us a sort of tool chest for building on top of, I can now use that to make open set algorithms out of other stuff. And later in the tutorial, and are we at the time of breaking yet, Walter?
Yeah, we're just at the break.
Just the break time? So when we come back after break, we'll actually go through examples where we walk through transforming known algorithms into open set versions of algorithms so you can sort of see how to make that work. And break.
Yeah, so we're going to take it down till 1, so